Well, good morning, everyone. So I'm Steve Cleary, and this is when we're going to start looking at doing a PEG parser using a source generator in C#. And this will be interesting because this is several new concepts for me. I have used PEG parsers several times in the past. They're fantastic for writing domain-specific languages if you need that. So I've used them probably 3 or 4 different times and really like the PEG parser approach. So when you write parsers, there are some awkward things that I think PEG makes a lot easier. But anyway, yeah, so today I'm going to be just kind of like talking about PEG parsers, my plans so far, take a look at the essentially hello world source generator that I've already got from over the weekend. And yeah, we'll get started and see what happens, because I have, unlike my other open source coding, I really have no idea what I'm doing here, and so it's just going to be very open. So any comments or chats, I'll try to keep an eye on that. Yeah, let's get going. So let's see. Here's the the PEG parser that I currently have, which actually isn't a PEG parser yet, but this is more like the hello world source analyzer or source generator. And as someone pointed out on Twitter to me, source generators are actually not what you want to use. You want to use incremental generators for performance reasons. So this is just a reworking of the original source generator hello world into a incremental generator hello world. So all I'm doing here is taking any files in the project in the solution that end with PEG, and I get the contents of those files, and then I say for each one of those contents I want to, but right now I'm doing up a PEG parser, which doesn't actually do much yet. Attempt to parse it, and then I stick out this generated code, which just right now just essentially says, here's the result of the parse out to the console. It doesn't really do anything yet. I am using the new C# raw strings in my source generator, which is pretty nice. I like these. Let's see. So the only other part of this is, so I've got a project over here, which is like a test project with a grammar that isn't even a grammar, it's just, some text. And then inside of this, the other thing that's necessary to get this working is for this grammar PEG file, it has to have this build action of analyzer additional file. And I'm hoping that there's a way to like put add a template or something so that you can say add a PEG grammar and it'll automatically set that for you, because otherwise it's a little awkward. But anyway, so the source generator shows up here as a type of analyzer, and so here's my source generator up here, and it's in this project here as a dependency here. And it does have to be added as a specific kind of dependency. This is all documented, and it's pretty straightforward. But at least for the project reference, you have to set these special variables. And presumably, when you distribute it in a NuGet package, you'll also have to do something special. I don't know. I've never written analyzers or anything like that before, so this is all new to me. But we'll cross that bridge when we come to it. So anyway, this whenever this grammar.peg changes, Visual Studio actually runs the source generator from this project and spits out this generated file. So if we jump back here, this is the file that I'm adding to the solution, whatever the PEG file's base name was, pegparser.g.cs, G is for generated, and then this is the actual generated file. And as you can see, it's only parsing out the first word. of this, and that's because my current PEG parser is really rather simple. I've just started like doing some really basic things and playing around with some of like what I might want a PEG parser to look like, but not really, no serious implementation here. This is all going to be reworked and thrown away over the next however long this takes me. So I did want to talk a little bit about PEG parsers in general. And I think the time is pretty much right for doing what I want to try with this project is a parser generator that has as one of its main goals a maintainable grammar, okay, which sounds kind of funny, but a lot of grammars are not maintainable. So here's the README for my project. A bunch of useful resources that I found over the weekend. And but here's the I actually wrote down the goals because this is so to kind of provide some guidance as far as like there's going to be a lot of decisions, design decisions and things like that we have to make. If you have any opinions, go ahead and drop it in the chat. And hello, Freddie and Andrew. I know Freddie's from Europe. I'm not sure where Andrew is, but yeah. Sorry, apologies to my American viewers because this is the only time that really works for me, and I know it's really early for most Americans. But anyway, so the goals here, I want maintainable grammars, right? That's one thing that grammars, if you've written grammars for DSLs before, the maintainability of the grammar is awkward. Because most people are not just maintaining a grammar. They've got lots of other work that they're doing, and the DSL is some small part of their solution. So the point I want to make is when you're writing a grammar, it requires like this kind of specific mindset, and I don't really have a good way to describe that. But when you're writing a grammar, then you're in that mindset, and you're like, okay, now I understand the rules of this grammar design system, right? And then when you're in that mindset, making changes to the grammar is relatively easy. So you do the initial development and everything like that in that mindset because you're in it all the time, and for days or whatever, you are in that mindset. And then you're done with your DSL, and you're like, okay, so I'm going to go off and work on my real project, and then weeks later, you find some edge case in your grammar that wasn't handled correctly, or you want better error handling is another common scenario with another common reason to change grammars, and then you have to revisit that grammar file, and you're like, I have no memory of this place, what? And it takes some time to re-enter that grammar writing mindset. And one of the problems with that is grammars. Historically, grammars have had, I think, two situations where. Freddie's in Australia. Sorry, Freddie. So there's two situations I think where grammars cause some maintainability issues. So the first one is left recursion. Okay, so in old school grammars, I grew up on Yak and Lex and those kinds of grammars. With those old school like LLK parsing grammars, left recursion is very difficult to work with, and what you end up having to rewrite your grammar to remove left recursion, because it turns out that I don't know if it's difficult or actually impossible in some cases for the actual parser generator to automatically rewrite left recursion rules. I don't remember, but many times when I've written grammars, you write the grammar that you want, and then you have to mangle it to remove all the left recursion. Well, there's been some recent developments in PEG grammars that allow automatic handling of left recursion, which is awesome. So we can look into that a little later in this series. So that problem has pretty much been solved. There is another problem that grammars have, and that's, I've been calling it in my notes bifurcation, but essentially it comes up often enough, and it's really annoying when you're writing the grammar. And that is, you've got here's the normal program structure. Here's how I want my DSL to look like, and then except for when this specific thing happens, then all the nodes underneath this have almost exactly the same structure, but not quite. There's one difference, right? So that is really annoying as a grammar writer, because you have to rewrite or duplicate all these rules, right? And now it's well, this is a function definition in this particular scenario, and here's a function definition, or here's my regular function definition, here's my function definition in this particular scenario, and it's just slightly different, and then that just really reduces the maintainability of grammars. So the goals, one of the primary goals of this project is maintainable grammars. I want usable, maintainable grammars, and more focused on how people really use them instead of most of the papers that you read about grammars are very, I don't want to say pie in the sky, but they're very academic, and they're just, they have some limitations that make them not really useful in practice. So I want to make them as useful as possible, and I want to talk to you a little bit more about that today too. And maintainable. So this is like a PEG grammar that's not just the core PEG grammar, which isn't really terribly useful, but actually has some extensions that make it far more useful. I'll talk more about that in just a minute with state. So another goal that I want to do is really avoid the constant string allocations that are common with a lot of grammars. So we've got spans in memory now. I'm not aware of any grammar parser generator that actually uses spans and memories yet. Probably for backwards compatibility reasons. As our whole API would change, it would be a breaking change. So I want this grammar, from the ground up, and let's use these and just and reduce that allocation as much as possible. So even in the ending nodes, I just want memories, right? Not strings. Okay, so implementation as a code generator, we got that. So this is all using the modern source. They're not source generators. They're incremental generators. But using the modern incremental generators, it's all current, MS Build, Roslyn, full cross-platform support. This should work on any platform. And I also want it to be reasonably efficient. So I'd like it. One of the problems with PEG parsers that you get into is that, so there's two things that cause inefficiency in PEG parsers. Core PEG parsers are extremely efficient, but there's two things that tend to cause inefficiencies. One is that left recursion, that automatic left recursion handling, because that it essentially, you have to reevaluate a rule over and over again in order to handle that left recursion. That one is not entirely avoidable, I think, as far as the execution hit you get. But what I want to say here is this goal is lower in the list. The maintainable grammars is higher in the list. So I want that left recursion automatically handled, even though technically it makes the grammar run in, I forget if it's exponential or polynomial time or whatever, but like the core like academic PEG grammars run in like linear time or something insanely fast. But to make them actually usable, they slow down. So left recursion is one. The other one that I want to talk about now is state, and this comes in where PEG grammars define a language that is again very academic, and it's just really useful to just kind of extend that language just a little bit and extend it just a little bit into the contextual language space, right? So you've got your context-free grammars that are that are a lot easier to parse. And we want to extend that a little bit into contextual grammars, just a little bit, because some of that is just so useful in the real world. And we can do that, I think, reasonably efficiently. That's where another big hit to the efficiency comes from in real-world PEG parsers, because pretty much every PEG parser allows that, just because it's so useful. And but then that causes your memoization to really explode in terms of space usage. So I'm going to be looking at some ideas I had over the weekend on how to really how to restrict that as much as possible. Make it as efficient as possible. But the goal is with this project is usable PEG parser, right? Not an academic one. So it sounds like I'm really against academics, but I'm really not. So actually, a lot of these, I've got a lot of papers in here that are referenced. I read every one of these, some of them several times over the weekend. Every one of these papers. So some of these things like the left recursion. So here's the actual left recursion academic paper, and the left recursion. The automatic left recursion reduction or solution depends on memorization. You can't get along without it. Some older PEG parsers would by default not memoize, which then has them run in non-linear time. But all of the modern PEG parser generators tend to memoize by default, and then you can turn it off if you want to. So I think I'm going to take that approach, also, especially because to solve that left recursion problem, you have to memoize. You can't turn it off those, or you just end up with a stack overflow. There's also been some interesting work on what's called a cut operator, and the original paper here. This is not the original paper because that's in Japanese and I don't speak Japanese. Maybe Andrew could help me out with that one. But one of the follow-up papers, the original paper was also by this author describing the original cut operator, and then this paper is like a follow-up paper where he discusses automatically inserting the cut operator. So I will look at that when the time comes. And today I want to focus in on state. This is what I've been thinking about a lot lately, because one of the problems with state, and I don't think I actually have I don't have a link to that in here. Okay. So let's talk about state, and I actually wrote this up in like a completely separate doc here, and all these doc files are actually what I had in my notes that I just typed out for the most part straight up. So here's things that you can't do in a regular PEG grammar that would be really nice to do. So, for example, if you're writing a light XML parser, you wouldn't want to write an actual XML parser in PEG, right? Real world usage, you would use an XML parser. But say if you have a language kind of like XML, where you've got like that, some kind of opening tag, ending tag, something like that, where you've got this you've parsed the opening tag, and now you need to parse a bunch of stuff until you get to an end tag that matches that opening tag. But there's not really a way to do that in PEG, because PEG is academic PEG, because PEG grammars are context free. So you can't say now parse these inner things, but not if it matches this thing that I've already seen, because this thing I've already seen is context. So a lot of times PEG grammars will permit a kind of state. That's what I'm calling it here in this project. So like when you parse that opening tag, then you set your state to some state variable or something like that, to say, I have now seen this tag, and now parse everything in here until you see the ending tag. So that kind of thing is useful for state, so state is one of the reasons people use state is to do that. Another reason, this is a common one that's mentioned more in the academic area, and that is forward declared identifiers, right? Some languages, you have to declare your variables or functions or whatever before you call them, because otherwise the grammar is ambiguous. You don't know if this is a function call or if it's actually like or whatever, So you need to keep track of those identifiers in order to know what you're actually parsing. Oh, that's the other thing that I wanted to mention. PEG grammars have this great ability to define the abstract syntax tree right from the syntax. So you don't have to parse it first and then transform it into an abstract syntax tree. And that is definitely something that I want to keep in this project. That is one of my, I would see that as the first goal, right? We're making it maintainable, we're making it usable in the real world. So another example is the new C# raw strings, right? Where a string can open with any number of double quotes, and then it ends with the same number of double quotes. Very similar to that. If you look at interpolation over raw strings, you can have any number of $ before the opening quotes, and then that number of $ is the number of opening braces and the number of closing braces within that string. Now, these are kind of the things that a basic PEG parser can't do. You have to have some kind of state to say, okay, we are now parsing a string that was opened with 4 double quotes, and it's being interpolated with 3, triple braces or whatever. And you have to have that state as you parse through it. Another example, significant white space. Okay, so the most common thing is Python has that indentation rules, where if it's indented at the same amount, then that's that defines where it is, instead of using curly braces, right? It's essentially the same. Logically, it's the same thing as curly braces. It's just using white space to determine what block a line of code is in. So I have done, oh man, that was a long time ago, but I have done significant white space parsing similar to Python before. That was probably Lex and Yak, not even a PEG grammar. But there's this nice trick you can do with where you Lex the white space into essentially like an indentation token or unindentation token, and then you can match those in your parser. Now in a PEG grammar, your lexer and your parser are the same thing. Yeah, well, I want to work out an example of that to really understand what I want to do with it. And then the final one, which I added kind of after the fact, is we can also use state to avoid what I'm calling bifurcation, right? Where you have, here's this set of rules, and then here's this set of rules that are almost the exact same thing, except one of these rules has a change, and because of that, all these other rules, that nest, also have to be like, well, I'm this rule in this particular situation. Whereas if we had some kind of like a Boolean state, we could actually avoid that, I think. As far as I know, no one has ever actually done this kind of extension, this kind of state extension. So I'm curious to know how well it works in practice, because I will actually be using it, I think, in my actual PEG grammar. Yes, I will, because state itself, supporting state itself bifurcates the grammar for the PEG. Wow, okay. I'm gonna have to like really be careful about terminology, but supporting the state, anyway. So supporting state itself bifurcates the grammar for the PEG grammar parsers. I think that's right. I'll show what I mean in just a minute. So one of the so I already talked about the second problem, that when you add state to a parser, normally when you're memoizing stuff, you're just like, okay, here I am in the input, and I'm parsing this rule. And those are the only things, right? If you look at all the academic PEG parsing literature, well, that's all you need to know. I'm at this state and I'm handling this rule. That's the only stuff that goes into your memorization cache. It's the only part of the keys. The problem with state is that it also, your state also needs to be stored in your memorization cache, or at the very least a decent hash of the state. I was thinking more over the weekend, and it seemed to me that if we have a sufficiently advanced hash like SHA-1, we could actually hash the state and store that as the key of the memorization cache, rather than storing the entire state. So anyway, so it will cause your cache to grow anyway. That's just minimizing the impact. But it's just the fact that you can parse, at the same rule at the same point in your input string, but have different state. So that just makes your cache much less useful. You're not getting the proper cache hits. There are ways to try to work with that. One of the papers that I discovered has some good advice there. And then the other problem is a lot of PEG parsers that allow state allow any kind of like arbitrary state. So you can say, okay, at this point in my parse, I want to like increment the state. Say if you're keeping track of some kind of, how deep am I in this thing? And if you just like add 1 to your state, for example, that kind of situations, if you have an arbitrary state modification at any point in your grammar, it can cause infinite left recursion. And there's actually Pegasus has a Pegasus has an example of this. In one of its open issues. And it's probably going to be an open issue forever because there's no actual way to solve it with arbitrary state, and Pegasus allows arbitrary state. Where are we at? Here we go. So here's an example of an expression. It's memoized, which you have to in order to get rid of this left recursion. And all right. So just to give an example here, so something that would actually work, and I'm just going to assume always memoization here. Something that would work would be like this. If you want to match, say like AAAB, all right? Or let's just do AAB. Okay, so the way that the regular parser would work. It would come into this expression and it would say, okay, so this is left recursion. It would detect left recursion and say, and at first it would just pretend like, oh, well, this one, I'm going to pretend this didn't match anything, and then I'm going to try to match A or B, and let's say this is just me. I think that's more the context here. No, okay. Yeah. All right. So anyway, I'm not terribly familiar with the left recursion solution, but essentially what happens is it'll keep on reevaluating this expression here until it doesn't consume anything else. So it'll go forward into A, it'll go forward into A, and eventually it'll try to go forward into A, back out, and then hit B. Okay. So the problem here with this pound state, and he just has an assignment here, which isn't that hard to handle, but it's really easy to change this into something like different. Well, now we're adding one to our state, right? So the state's always different. And in this case, because like the hash state here, which is Pegasus's way of running state code, state modification code, without consuming any input. That's the key. So the problem here is this breaks that left recursion handling, because now every time it left recurses into this rule, the left recursion depends on, have I seen this, have I tried this rule at this point in this grammar before? And that's how the left recursion is handled in PEG grammars. And this breaks that because now you're updating the state. And so now, every time you re-enter this rule, the left recursion, algorithm is checking, have I been have I seen this rule at this point in the input string before? And the answer is no, because your memorization key is different, because the state is different. So it thinks, well, I haven't seen this before. And as long as that's true, it keeps on left recursing, and then you end up with a stack overflow. So essentially, state can break the left recursion algorithm. So the question is this actually solvable? And that one I'm not sure about. One of the papers that I found, actually I'm going to grab this issue and link this over here. So one of the papers that I found is, it introduces this idea called vPEG, which this is a useful paper to look at because it illustrates several things. This one. So there's a couple things that I'm not fond of in this paper, but they have some great ideas. And one of them is, so they define like this idea of a vPEG, or like essentially a parsing expression grammar with variable bindings. That's what they define it as. And I'm going to take like that same kind of idea, I think, in my parser, and I'm really thinking like way ahead here because I haven't even parsed anything yet. Yeah, so they've got several examples here of, hey, if we're trying to match an XML-like language, then we really need some kind of state here, some kind of variable. They explain several of the problems with stateful packrat parsing, which is essentially like what Pegasus does, where you can have any kind of state in there. There is, so we've got some context-sensitive features, all right, in real-world grammars. In other words, this is how people actually use them, right? We're leaving the academia world a little bit here. So it talks about that, and then we have an explanation here that they have an example here that, it's not, we're leaving way behind the linear parsing that you get from a standard pack-rat parser doing a PEG grammar in academia, right? Because nobody actually uses it that way in the real world, except for really, really simple grammars. So they have an example here of where you can actually get exponential running time, okay, which is pretty bad. And then they have this, essentially they have this idea, and here's, to reduce it down to polynomial time. Now, in order to do this, they don't allow arbitrary state. That's the key point. Instead, they just have these, they split it up into two different states, and then they define these operators on those state variables. So you can so essentially, I won't go through the entire paper explaining this, but the entire idea here is that they end up with, here we go, let's see if we can do, I don't know if they really explain that part in here. No, okay. So they go on to that part of the paper is we don't need yet. Just looking for where they define the bind things. Okay, here we go. So here's the explanation of how they do their binding, and essentially what it comes down to is they're defining two different kind of states, and it's completely different. So they've got what they call a match state, and they have what they call an exist state. So we've got exists and we've got match, and then they have one scope operator, which really only affects match for reasons that I will explain in just a moment. So essentially, what they're doing is instead of saying you can set any state at any time to whatever you want, which is the way most PEG parsers are implemented, and which breaks left recursion, they're saying, all right, there's two different ways you can use state. You can either match, so in other words, I saw this thing earlier and now I want to match the same thing later. So you've got like that XML beginning and end tags. Raw strings I open with 4 quotes. They're going to close with 4 quotes. With a little bit of further extension, you can also say things like I opened with I opened 3 braces with this expression. It has to close with 3 braces. If you're doing like interpolated raw strings, that kind of thing. Changing the match isn't actually supported by the process in this paper, but it's not hard to add. So you've got like this kind of like a back reference, right? To use regular expression terminology. This is a back reference. Perfect example, by the way. Regular expressions have all kinds of extensions in them that make them not regular. Right? Because regular languages are actually a subset of the languages that a PEG parser can parse. But if you look at like the actual regex operators, which is what people actually use them as, character escapes are fine, character classes are fine, anchors are fine, grouping is fine, some of the grouping is fine, I should say that. Okay, so you've got like sub-expressions are fine, naming groups are fine. These positive look-aheads, negative look-aheads, this is no longer regular grammars at this point, right? Because now you're talking like arbitrary look-ahead in the input string, which is not something that a regular expression grammar can actually handle. And quantifiers are fine. Here we go, back references. Back references, again, not allowed in regular grammars. If you look at like the actual academia, what's an actual regular grammar and a regular expression, these are not part of them. But they're so useful, right? That every regular expression library in the world supports back references and things like that, and positive and negative look ahead. They're so useful that that people implement them anyway. So that's kind of like what I'm talking about with, well, yeah, you know, the PEG grammar in academia is very restrictive, but then people in the real world extend it with things like state and stuff like that. So it's not actually a PEG grammar. It's like a PEG grammar plus some contextual, some useful contextual aspects as well. So anyway, so we've got the match and the exists are completely different types of state here. The match is like a back reference. The exists is like that forward declaration. Now, the problem is, and here's where I disagree with the paper here. In order to get like some of these, I think that they did it in order to make their example parser look good on the benchmarks, but essentially exists is not implemented in a useful way in this paper. They define the exists here as being the exists operator as being globally memoized. And what that means is if you were to actually like implement the ideas in this paper and you saw, and imagine you're like parsing through something a little bit more complex. So there's two problems, right? First off, there's no scoping, really. If you had multiple functions and each of those functions declared a local variable, then that doesn't work with this. That doesn't work with their implementation of exists, because those variables would continue to exist outside of the scope of that local function. So like if you're doing something like variable hoisting, like the old style JavaScript used to do, that would actually work with this kind of exists. But if you're talking local variables, no. Local variables just don't work with this kind of grammar approach. And the other problem is, imagine if you have like a fairly complex grammar, again for like a C style language, that's the point of them adding the exists operator in the first place, is these forward declarations. Then what you end up with is a situation where you can end up parsing into something as though it were a declaration, realize later it's not a declaration, back out, the parser backs out and parses it as something else and then continues parsing. Well, because of the global memoization of exists in this paper, that is actually still a declaration in the rest of the program. Even though it's not a declaration, it's still treated as a declaration. So so in this paper I have serious issues with the way that they implement exists. And then they do things like, well, because it's globally memoized, it doesn't have to be in the cache and in the memoization cache, which would be true. But like I said, those problems, the lack of scoping and the problems with backtracking, not undoing those declarations, really make the exists operator and the entire exists state, as they define it here, useless in a real world PEG grammar generator. Okay, so just get that out of the way. I don't really like how they did the exists there. But what I do like, and it took me a while to like this, I did not like how they split the state up into two different things, like match and exists. But on further thought, this last weekend, I think that does make sense. And in fact, what I end up in my state, design document, if you want to call it that, is actually three different sections of state instead of just two. So one other thing that I wanted to point out before I leave that paper is this is an example here. So here's their actual like grammar of the vPEGs, and here's a perfect example of bifurcation. All right, so here's all your regular PEG grammar constructs. This is all the stuff that's very common in every single PEG grammar, and then we've got this idea of binding some variable to some expression, the result of some expression. Okay? That totally makes sense, but within that expression, it can't just be anything. It can't be any expression, because we don't want to have like a bind a variable that then inside of that expression has another bind, right? How would you even handle that? So instead of, so it can't say, any expression. It has to be, well, this is an expression, this E of P. So this is like the original PEG, all right? And then we've got this completely separate, not separate, but like this same grammar. And if you look at this, it's the exact same thing as all this stuff up here, right? So we've got, well, they don't do the forward look aheads. That's interesting. I guess that does make sense. Anyway, so there's a couple changes. You can't do forward look aheads, right? The and EP is missing here. And then you can't do any kind of like bind or match or anything. I think you could do match. I don't see why you wouldn't have a match down here. But anyway, you can't do scoping, or you can't define a scope inside of a variable value or anything like that. So you've got like this restrictive grammar, and this is a perfect example of grammar bifurcation, right? Where you've got, here's what I really want. I just want, this E to replace all of these E of P's up here. That's what I really want, but I can't quite do that. So there's like this am I within a bind expression, like Boolean variable, right? That we can treat it as a Boolean variable, and then have things like this one would say, well, you can only include a bind if you're not already in a bind expression, right? So you can put like a negative, some kind of negative conditional on that Boolean variable and say, well, you can only match this bind if you're not already in a bind expression, if we're not in that context, right? So that would really simplify this grammar. And, this happens a lot when you're designing grammars, where you have some kind of scenario where you want it to be exactly like a regular expression, except for this one or two changes, right? So I added a third kind of state specifically to handle that. And this is just for grammar maintainability. And like I said, I don't think anybody else has ever actually done that. But the idea is we end up with 3 different kinds of state now. So let's see here. Okay. So if you look at the kind of state that I want to end up with, and this is again a restrictive state that will hopefully still allow yes, it will still allow left recursion to work, I think. I'm going to walk through that in just a minute because I didn't actually think all the way through that. Yeah, so let's see. Okay, so we've got backref, which is essentially the match from the vPEG. We've got set. Now set, I didn't really look at that part of the paper, but the exists is useful. That is a useful kind of state. It's just that the way that they treat it in this paper is not useful. So having that as a separate state and having it with essentially the same semantics, which is like this set of symbols instead of like a single match, it's a set of symbols that you've seen. But we want it to work with backtracking and scoping. So so what I'm calling set is essentially the same idea as exists, except it's actually going to be useful in real world grammars. And then I added this Boolean one, which is just for to avoid grammar bifurcation, and that one might actually not work. I gotta think about that. Okay, so backref. Here's the syntax that I kind of ended up with that I'm thinking of. So we can set it. I'm just thinking how these would all work. What we want to avoid is this this kind of situation here that would prevent this from working. Any kind of a zero length state changing statements can break left recursion handling. So I want to walk through these really quickly and just see if any of them can break. All right, so if we have something like this, we're setting the name to some expression, then this will not break left recursion because this will match. Okay, so we have to, well, it can match nothing, right? But if it matches nothing, then the next time that this is recursed into, it will have already been seen, right? And that state already exists. That name won't change. So that's fine. It would recurse one extra time if it matched nothing, but it would still actually work. Okay, so let's talk a back reference. Would actually match a literal string, which again might be nothing, which would be fine. Again, it would recurse one, well, no, it wouldn't even recurse one extra time. It would just match nothing and then work. Yes. Okay, backref scoping. Can we scope into it itself? Let me see. Yeah, because that doesn't actually change the state at all. Okay. And then this backslash name with coding is just a way to like modify what we're matching against. So that has the same semantics as this one. All right, so let's see. So let's talk about set state. So set state is keeping track of a set of strings as we go along. So this one uses, I gave it like the tilde syntax. I'm still not wild about the tilde, but so in this case, we would be matching an expression, possibly empty. I don't know if I want to allow white space there. Anyway, be matching an expression, possibly empty. That would also work for the same reasons. And when it recurses again, you know, it would, even if it's empty, it wouldn't be changing the state again on the second time through. So it might recurse an extra time, but it would work fine. So this one, if we match input, okay, so this one, we're matching input again and testing if it's in that set. If it is, that's the empty string, then regardless of whether it's in there. Okay, yeah, so that would also work. And the set scope, same thing as before, doesn't really matter. Okay, now the Boolean ones I'm not as sure about, because then we've got, oh yeah, those would work. Those would totally work. Because we've got set this Boolean, you know, value, just and this would be like something like when we're doing a name binding, for example, and we want to set it to some expression. If we want to disallow other name bindings, we can say something like in name binding or something like that. So this would actually set this Boolean variable for the scope of this expression. And then this is still like, you know, checking out the left recursion rules. The first time it would set it, go into it and say, well, now it's set, so I have to reevaluate it being set, and then it would set it again, which wouldn't actually change the state, and then it would detect that that's the end of that recursion, that it's been there before. Okay, so that would also work. Same thing with unsetting if we have that syntax. I'm not sure if we need an unset. And then finally, are we in the name binding? So this is a 0 length match, but it would always be the same. Yeah. Okay. So I think what I have here, pretty sure, is a way to allow state, but not arbitrary state. I've got 3 different kinds of state: back references, where you match something you've seen before. I've got sets where you can say, you can add this match to this set. The variable is always a set. And then you can check to see, is it the set? Or is this new match in this set or not? And then Boolean state, which is really just set this Boolean for this scope, and is this Boolean set? And all three of those avoid the problem, I'm pretty sure, avoid the problem of arbitrary state breaking the automatic handling of left recursion. Okay. So that was a huge memory dump. It was a huge thought dump of what I've been thinking about this weekend. And yeah. All right. So I haven't actually done any coding. But from here on out, I think we're going to start coding and start actually implementing this PEG grammar. All right, so how's the PEG grammar going to look? I already kind of started some ideas here, although I think that, I've got like these higher order functions with these, they're taking functions and passing functions back that are modified. I'm not sure if those will actually work as PEG grammar output. We will see. These might actually need to be like generated code instead of just like higher order functions. I've also got this parse result, which might change, because what I don't have in here at all yet is any kind of representation of state. So we've got this, here's an example of what I'm thinking of for the parse result. And I'm leaning pretty heavily on structs, tuples, read-only memory. It has to be memory and not span, because for things like the memorization cache, we actually have to like hold on to it in a data structure. So for that reason, like I was originally thinking, we should just do a PEG parser over spans, but I don't think that's really possible. Has to be over memories. So I've got like a pretty basic parser working here, an extremely basic parser. It can parse one. I don't even have like this is me experimenting with a parse result of a type, so it can actually return some kind of value, which we are going to need eventually. Oh, and I did actually start looking at some parse state, but this is completely wrong, and I'm going to be changing that. That's arbitrary state right there. And I was like, wait a minute, that's not going to work. Okay, so what we have right now is, these are pretty much all the, this is just me writing out the syntax, going through the syntax, what I'm thinking for the syntax here, and except for cut. I haven't even looked at cut yet. But I think pretty much everything else is, and attributes, I haven't done anything with those yet, and types. But all of the actual core grammar here, I think is already represented here, just as like concepts, right? This is how I kind of want it to work. They're not actually being used at all yet. So right now, the PEG parser just works by looking for a single identifier, and I define an identifier as, so here's like what the grammar would look like in this comment, right? And then here's what it looks like using these higher order functions. It's pretty nice because you can actually kind of see the grammar here, where you've got the first letter is a lowercase letter or uppercase letter or underscore, and then other letters are any number of lowercase, uppercase, underscore, digit. Your pretty standard identifier there. So then it builds this parser by composing these higher order functions and then it runs the parser on the input. Now so the thing that I'm thinking is I'm not really sure if these higher order functions are going to actually exist in the final product. It might just be they might just be code generation patterns instead. But this is like the general idea of where I'm going. So it matches a single identifier, and that's why you've got like this this result, and it just matches the first word because it doesn't understand any kind of white space or spaces or anything like that. But you can say, you can change it, not even save it. You don't even save it, and it automatically like regenerates. So the source code stuff is all hooked up and working. Changed it back to this. So yeah, I'm at time. I'm going to go to work now. But this has been me describing my plans and my goals with this. And tomorrow morning, I'm going to start coding this thing. And we will see what that looks like. My goal, so what I want to eventually get to, and I don't know if this is really possible with source generators, but what I want to do is have the PEG parser generator get to a point where it can generate the PEG parser generator, which is kind of crazy. I don't think I can do that. I think what I'll have to do is have the PEG parser generator get to a point where it can generate an abstract syntax tree of the PEG grammar, and then have some other object transform that AST into an actual PEG grammar generator. Pretty sure that's what I would have to do. Okay, so we're going to definitely end up with an AST, almost for sure. So I'm going to start, but like bootstrapping, right? This is the hard part. Like, how do you actually get it to? I wrote all this by hand, obviously. So like right now, I'm not to the point where I can use its own output, and it might be a little while before I actually get it to the point where I can bootstrap. But I'll think about that, see which parts of the PEG grammar are simpler and we can do first, like the identifier. And we'll see how long it takes before we can actually bootstrap. This will be interesting. I have no idea how this is going to work out, but thank you all for joining me. I'm going to call it for today, and we'll see you next time. Have a great day.